4 things about plutonium that will genuinely unsettle you. Why a brand new reactor suddenly poisoned itself to death. What flaw nearly made the plutonium bomb impossible to build. How 6 kilograms of metal can fit in your hand yet level a city. Why 500 tons of separated plutonium still has no agreed solution. There is an element on the periodic table that does not occur in nature in any meaningful amount. You cannot mine it. You cannot find it in a riverbed or a mountain. To get it, you have to build it atom by atom inside a nuclear reactor. That element is plutonium. And the process of making it is one of the most technically demanding things human beings have ever attempted. A single kilogram took the combined effort of tens of thousands of scientists, engineers, and workers across multiple states. A single microgram inhaled can cause cancer. Yet we made tons of it. To understand how plutonium is made, you first need to understand what it actually is. Plutonium is element 94, which means its nucleus contains 94 protons. It sits just 2 steps above uranium on the periodic table. Uranium is element 92. The gap between them is not empty. It is crossed by a precise sequence of nuclear reactions, each one transforming one element into something slightly heavier. That transformation happens inside a reactor under controlled conditions using uranium fuel. The physics behind it was understood by 1940. The engineering required to actually do it took another 4 years and billions of dollars to figure out. The story begins with Glenn Seaborg. In 1940, Seaborg was a 28-year-old chemist at the University of California, Berkeley. He and his colleagues were bombarding uranium with deuterons, heavy hydrogen nuclei, in a particle accelerator called the cyclotron. On February 23, 1941, they confirmed they had produced a new element. They named it plutonium after the planet Pluto, following the convention set by uranium and neptunium. Seaborg would later say it was the most important discovery of his life. At the time, though, only a microscopic amount existed, about 1 microgram, invisible to the naked eye, detectable only by its radioactivity. What made plutonium immediately significant was one physical property. Plutonium-239, the specific isotope that Seaborg's team had confirmed as fissile after first discovering plutonium-238 was fissile. That means a slow neutron can split its nucleus, releasing energy and more neutrons. Uranium-235 is also fissile, but it makes up less than 1% of natural uranium. Plutonium-239, made from the far more abundant uranium-238, could theoretically be produced in large quantities, and a chain reaction in plutonium-239 could in principle release an enormous amount of energy in a very short time. Seaborg understood this. Within weeks of his discovery, he wrote a confidential memo to the government outlining what the element might be capable of. By late 1941, the United States government was already funding nuclear research under a loose program called the Uranium Committee. After Pearl Harbor, that program was reorganized and massively expanded. It became the Manhattan Project. The core problem was simple. The only way to make plutonium in useful quantities was to build a reactor, a sustained controlled nuclear chain reaction. And nobody had ever built one. The physics said it was possible, but the engineering had never been attempted at any scale. The first task was to prove the basic idea. That job fell to Enrico Fermi, a physicist who had recently arrived from Italy. On December 2, 1942, Fermi and his team achieved the world's first controlled nuclear chain reaction. The location was a squash court under the stands of Stagg Field at the University of Chicago. The reactor, called Chicago Pile 1, was made of 45,000 graphite blocks and approximately 93,000 pounds of uranium in metal and oxide form, stacked by hand over 6 weeks. When cadmium control rods were slowly withdrawn that afternoon, neutron detectors climbed steadily. The reaction was self-sustaining. Fermi let it run for 28 minutes, then ordered the rods reinserted. A coded phone call was placed. The Italian navigator has just landed in the New World. Plutonium production was now theoretically within reach. Chicago Pile 1 proved the concept, but it produced almost no plutonium, a fraction of a microgram, nowhere near the kilogram scale a weapon would need. To produce plutonium in weapons quantities, you needed a reactor running at far higher power. You needed cooling. You needed a way to handle the intensely radioactive spent fuel afterward, and you needed somewhere remote enough that if something went wrong, It would not take a city with it. The Manhattan Project chose a site on the Columbia River in eastern Washington state. Flat, cold, remote. A small agricultural town called Hanford was cleared. Its residents were given 30 days to leave. Construction at Hanford began in March 1943. Within 18 months, a workforce of 50,000 had built a small city in the desert. The centerpiece was 3 production reactors, each one a massive graphite cube. The largest, the B reactor, contained 2004 horizontal channels for uranium fuel slugs. Those channels passed through the graphite moderator and were cooled by river water pumped directly from the Columbia. The reactor core measured roughly 28 by 36 feet in cross-section and 36 feet tall. A large rectangular graphite block the size of a large house, threaded with aluminum pipes, sitting behind concrete walls several feet thick. Nothing like it had ever existed. Engineers were building from scratch in real time using physics that was barely 2 years old. The fuel that fed these reactors was uranium metal. Specifically natural uranium, mostly uranium-238 with a small fraction of uranium-235. It was pressed into cylindrical slugs, roughly the size and shape of a roll of coins. Each slug was canned in aluminum to prevent the uranium from reacting with the cooling water. Thousands of these slugs were loaded horizontally into the reactor's channels. Inside the reactor, neutrons from the fission of uranium-235 were absorbed by the far more abundant uranium-238 nuclei. That absorption transformed uranium-238 into neptunium-239. Neptunium-239 was unstable, and within 2 to 3 days it decayed into plutonium-239. The reactor was, in essence, a continuous transmutation machine. The process sounds straightforward on paper. In practice, the engineering was brutal. The reactors had to run continuously at high power while remaining stable. They had to be loaded and unloaded while running. And the irradiated fuel slugs that came out of the reactor were extraordinarily dangerous, far more radioactive than anything that had gone in. Each slug now contained plutonium, yes, but it also contained hundreds of radioactive fish byproducts, cesium, strontium, iodine, and dozens of other isotopes. To get to the plutonium, chemists had to dissolve the entire slug in acid, then separate plutonium from uranium and from all of those fission products. That separation process had to be done remotely behind thick shielding without anyone in the room. Glenn Seaborg solved the chemistry problem. Working at the metallurgical laboratory in Chicago, Seaborg and his team developed a process called bismuth phosphate precipitation. In this process, the dissolved uranium fuel was treated with chemicals that caused the plutonium to selectively bond with bismuth phosphate crystals. The crystals could then be filtered out of solution, carrying the plutonium with them. The remaining liquid held the uranium and most of the fish products. By repeating the cycle several times, plutonium could be progressively concentrated and purified. It worked, but it had never been tested above the microgram scale. Hanford would need to run it continuously on tons of irradiated uranium. It was a calculated bet on chemistry that had only been proven on amounts too small to see. The separation buildings at Hanford were called canyon buildings. They were concrete structures roughly 800 feet long and 65 feet wide, built without windows, their walls 8 feet thick. Inside were rows of enormous stainless steel tanks called cells, where the chemical processing took place. Operators could not enter. Instead, they controlled the process from above, looking down through thick glass windows using remote cranes and manipulators. The scale was unlike anything in industrial chemistry. Nothing had been designed, built, or operated this way before. When the first canyon building, called Tlant, began operations in late 1944, it was the largest building in the world and one of the most dangerous places on Earth. Then the first reactor ran into a problem nobody had predicted. When the B reactor was started up for the first time in September 1944, it ran for 12 hours. Then the power began to drop. The reactor was poisoning itself. Physicist John Wheeler quickly identified the cause. Xenon-135, a fission product that absorbs neutrons extremely efficiently. As it built up inside the reactor, it was soaking up neutrons faster than the chain reaction could sustain itself. The reactor had effectively shut itself down. Fortunately, the reactor had been built with extra fuel channels. a design choice the project's engineers had insisted on, almost as a precaution over objections that had added unnecessary cost. Those extra channels were now essential. Loading them with additional uranium fuel was enough to overcome the xenon poisoning. By early 1945, all 3 Hanford reactors were running, and the canyon buildings were processing fuel. Plutonium was being produced in kilogram quantities. The irradiated fuel slugs were pushed out of the back of the reactor by new slugs fed in from the front.